4 minutes and then we can start.
Sure, yeah.
So Girish, just also let you know the talk will be recorded, so there are no issues with that, right? Okay.
Dipanjan, this is now second workshop which we have had in the Indian community on computing.
This is the second workshop, and this is more of a connection between the technical group members of the NSM as well as from the ANA community.
It's really nice.
Yes, I hope you do stick around for the panel discussion. That will be. I'm personally looking forward to it.
Yeah, I'll make sure I'll be there. Yeah, sounds very interesting.
Yes. Okay, so it's 2. Maybe we can start now and then let people join in. So welcome everybody for this afternoon session of today, where we are now focusing on talks and lectures on astronomy and astrophysics and applications of HPC in astronomy and astrophysics. So this afternoon we'll have 2 talks, and the first one, it's our pleasure to welcome Professor Girish Kulkarni from the Tata Institute of Fundamental Research to talk about cosmological simulations and radiative transfer, and how people do radiative transfer in such large-scale simulations. These are extremely complex and challenging problems requiring a lot of HPC usage, and I'm sure Girish will give you a flavor of what things are. So Girish, please take over.
Great, thanks Dipanjan. And it's really nice to see such a large audience in this workshop. So I should thank to all organizers, in fact, for inviting me to speak today, and also for organizing this workshop. I think Indian astrophysics community is still a bit behind the competition in terms of our computing capability, and workshops like this are important steps towards correcting that. So I congratulate all the organizers and all the participants for this workshop. What I'm going to talk about, as Dipanjan said, is cosmological radiative transfer simulations. I realize that not all of you are cosmologists or even astrophysicists, so I'll try to describe what these simulations are, what they are useful for, and what computational setup is used in doing these simulations and so forth. And then beyond the discussions about the computing, the scientific computing aspects, I will also show some science results in this talk, and those science results have been developed in collaboration with many individuals, all of whom are listed here on my title slide. Yeah. Right. So we really have to start by asking what cosmological radiative transfer is and why are we interested in it. So as many of you might know, we now have a reasonably successful model to describe the evolution of our universe, right? The so-called Big Bang model or the lambda CDM model. And the cartoon diagram that I have shown on this slide illustrates the evolution of the universe according to this model. So what is shown here on the right-hand side is the Big Bang, and then the universe starts from the Big Bang and evolves to the left-hand side of the diagram to today's universe, full of stars and galaxies and so forth, right? So the age of the universe is 0 at the right edge of the top of the plot, and it is 13.6 billion years on the left edge in today's universe. Okay, between these two extremes, there are several milestones in the evolution of the universe. For example, one milestone is the formation of the CMB, the cosmic microwave background, which is formed at when the universe is about 400,000 years old. Okay, which I have marked here as CMB. Then after that, there is another milestone, which is the formation of the first star, the first complex astrophysical object in the universe. We don't know exactly when that happened. We haven't seen the first star yet, so I cannot put a redshift or time label here. But then there is another milestone, which is when all the gas content, most of which is hydrogen, so all the hydrogen content of the universe is ionized, so that the universe changes from a cold gaseous universe to a hot universe at around the 1 billion year mark. So there are these various time steps with which the universe evolves from the Big Bang to its form today, right? The period between the formation of the CMB and the formation of the first star is colloquially referred to as dark ages, because there are no complex sources of light in this period. And then the period from the first star to the point at which all the cosmological hydrogen distribution is ionized is called reionization, right? For obvious reason, because hydrogen is reionized from the photons coming from these galaxies and stars. So this is how the universe, this is the picture that we have of the evolution of the universe. And what is apparent in the way I have described this is the role that radiation plays, right? Radiation clearly plays an important role in this story, because it is the radiation from these stars and galaxies that sets the thermal and ionization evolution of the universe, right? So what we do in cosmological radiative transfer is we want to compute the cosmological propagation of radiation from these individual galaxies and even black holes out to cosmological distances. And the reason we want to do this is because this radiation sets the thermal and ionization properties of the universe, and the thermal and ionization properties of the universe in turn sets the formation of galaxies and black holes, right? So although the total energy density in the radiation might not be significant, the radiation plays a very important role in the evolution of the universe here, particularly during the epoch of reionization. So this is what cosmological radiative transfer means. This is what we want to compute numerically on computers, and this is the reason we are interested in it. So how do we do this? We do this by means of the cosmological radiative transfer equation. Okay? So when we say we want to do cosmological radiative transfer, we essentially want to solve this equation in a cosmological volume in a computer. And so the way we can understand this equation, the simplest way of understanding it, is perhaps the geometry that I have sketched in this diagram on this slide, where I have a source, a little star that I have drawn here, and an observer here on Earth with a telescope and a spectrometer. And you will notice that when this observer sees this source, you basically have a ray of light or a sight line along which the radiation from this source travels to this observer. And while this radiation is traveling, it interacts with the material along the sight lines in the whole universe. And so what radiative transfer equation tries to do is compute how the total flux of this object, the radiation, the brightness of this object, evolves as you move along this sight line from the object to the observer. And you want to now do this in the presence of many, many objects. This is done by defining something called the specific intensity, which I have denoted here as I nu. And this I nu is a function of time, position, and direction. It's a complicated quantity, but radiation can best be described in terms of this quantity I nu, because it has this nice property that I nu is conserved along rays of light in vacuum. Okay, so if no absorption or emission takes place along this sight line, then we can be sure that the I nu that the source had produced is the I nu that the observer will see. Okay, so now what the cosmological radiative transfer equation does is that it writes down an equation for the evolution of I nu in an expanding universe. And this equation is written on at the bottom of this slide. This is a complicated looking partial differential equation where you have 3 terms on the left hand side and 2 terms on the right hand side. Okay, so we can conceptually understand these terms quite readily. For example, the first term on the left hand side is describing the temporal evolution of the specific intensity I nu. You have a del del t term here. The second term is describing the spatial evolution of the specific intensity I nu. The third term is a complicated combination of quantities, and it actually describes the effect that cosmic expansion has on I nu. So this term will just be 0 if the universe was not expanding. And on the right hand side, you have 2 terms, one of which has this quantity kappa, which quantifies the absorption processes along the sight line. So there are things that might be removing photons from the sight line because of various absorption processes. That is accounted by this term. And then the final term is this term J, which accounts for emission processes, including emission from the original source, but also perhaps secondary emission from other sources along the sight line, right? So the conceptual description of the radiative transfer equation is quite simple. It is just saying that the change in I nu is equal to a combination of emission and absorption processes, except that this conceptually simple equation is in fact a very complicated 6-dimensional partial differential equation. And so when we want to do computational radiative transfer, what we actually want to do is solve this very complicated partial differential equation on large cosmological volume inside our computer. Now doing that turns out to be very, very hard. And there are 2 main challenges why it is so hard. The first is what I would call the dynamical range challenge. Okay, and in this problem, what happens is that the scales on which you want to solve this partial differential equation, the scales on which you want to compute this I nu in cosmology are very large. They are usually hundreds of megaparsecs. But the scales at which the kappa and J terms operate, the absorption and emission terms operate, are very small. They are smaller than a kiloparsec. So in other words, you have 2 scales in the problem, the difference between which is about 4 or 5 orders of magnitude. So what this means is that when you try to solve this problem computationally, the problem is really, really large. You need a lot of memory simply to fit the problem inside the computer. Okay, and here is an example. What I am showing here in this figure on this slide is a slice from the cosmological density distribution of gas from a numerical cosmological simulation at redshift of 6. Okay, so then the universe was 1 billion years old roughly. So the color denotes the density in some units. And you will see that the plot has about the size of 160 megaparsecs over H, which is about 200 megaparsecs. And you see that the density distribution shows the interesting features like filaments, voids, and overdensities, which you might be familiar with if you do any cosmology at all. But what is remarkable is that the slice itself is about a couple hundred megaparsecs, but the sources and the absorbers of radiation in this slice are less than a pixel of this screen. Okay, they live inside those tiny filaments that you are seeing. So in other words, now the computational scheme has to keep track of what's happening at those extremely small scale and also on what's happening at these very large scale. That is the problem of dynamic range. This problem doesn't necessarily exist in other cosmological calculations, but it is a very serious problem in radiative transfer. But this is not the only challenge. There is a second challenge why cosmological radiative transfer is very hard. And this second challenge is because it's radiation. We have a speed of light involved. Radiation travels very fast. which means that any numerical time steps that you can incorporate in the algorithm have to be really small. Okay, whatever spatial resolution you have, delta x, the time step had better be about delta x by c. Otherwise, you would quickly accumulate numerical error. So what this means is that when you want to do computation over millions and billions of years for a cosmological computation, a small time step would mean a lot of CPU or computing time, because the computing task is going to take a long time. So these two challenges mean that the problem is really big and the problem is really long. Okay, so this is almost a worst case scenario for any computational physics problem, but there we are. That's what we face when we want to do cosmological radiative transfer. So people have tried to respond to these two challenges by coming up with several algorithms. Many such algorithms for cosmological radiative transfer have been developed over the last 15 to 20 years. But all of these algorithms, in my opinion, can be divided into two categories. Okay, in one category, I put all the algorithms that I label roughly as ray tracing algorithms. And the other algorithms, the other category of algorithms I called moment-based algorithms. So you have these two categories of radiative transfer approaches, ray tracing and moment-based. And most of the developmental work in cosmological radiative transfer have happened in these two directions. You will notice that most of this work is very recent. Unlike other numerical problems in cosmology, radiative transfer was simply not possible until big enough computers became available. Anyway, so what are these two approaches? In the ray tracing approach, what you do in your algorithm is you actually trace rays from each source in your cosmological box to each point in the box. And then you solve your partial differential equation along that ray, along each ray. This approach has the advantage that it is very easy to understand. We can easily think in terms of rays and how they interact with each other and so forth. And the approach has a property that the total time taken by this computation scales as the number of cells, number of Cartesian cells in your cosmological box times the number of radiation sources that you have in your box. So it scales as order n cells times n sources. The more sources you have, the slower the computation will be. Now, this is a big problem for cosmological radiative transfer, because in cosmology, a typical box will have millions to billions of sources. So simply the n sources term here, regardless of what n cells is, will slow your computation down significantly. So this is how ray tracing is. An examples of ray tracing are codes like C2Ray, Licorice, and Crash. Okay, these are all published codes that you can revisit in the literature. A second alternative which people have considered for radiative transfer is what I call moment-based approach to radiative transfer. And in this, you actually, instead of solving the real radiative transfer equation, you solve its angular moments. You only solve some averages of the radiative transfer equation. So in practice, you solve the monopole and dipole angular moments. I will describe this in greater detail in a few minutes. But the advantage of these moment-based methods is that the complexity of the algorithm, the computing time of the problem, scales only with the number of cells, only as order n cells. It is independent of the number of sources. That's a killer feature when it comes to cosmology. Now it doesn't matter how many sources you have, the code will take the same amount of time. It will only depend on the size of the box. And this also has been implemented in various codes now. An example is Aton, another example is Enzo RT, and a third example is ART. Okay, these are also published codes. So these are the two approaches. I'm not aware of a third approach that people have so far tried in cosmological radiative transfer. And in my work, what I have done is I have applied moment-based radiative transfer to cosmological problems. And so what I will do in the remainder of this talk is I will first describe one particular moment-based algorithm, and then I will describe how I use that moment-based algorithm, and I will end the talk by showing you 3 specific scientific results that I have obtained by using it. Okay. So we start by describing a particular algorithm. So how does this moment-based RT work? The way I was just saying, instead of solving this complicated looking partial differential equation, moment-based RT says that we will reduce the dimensionality of the problem. Instead of solving the 6-dimensional PDE, we will reduce the dimensionality of the problem by taking averages of the equation and solving those averages. And the catch is, the cost is that during the taking of these averages, you will end up making some assumptions. And these assumptions may or may not be valid. So that is your job to check if the assumptions are sensible, reasonable to you, whether you like those assumptions or not. But if you do like those assumptions, then moment-based RT produces these interesting average equations instead of the full radiative transfer equation. So we can begin to see how this works by writing down our radiative transfer equation, which I wrote down a couple slides ago, except that here I start by first neglecting the Hubble term just to simplify the discussion. So you might remember that this is how the radiative transfer equation looks. And if I neglect the Hubble term, this radiative transfer equation becomes much simpler, right? We now have just a time derivative term, a space derivative term, and on the right hand side, we have the absorption term and the emission term. So this is what we want to solve, right? So what moment-based RT does is it says I'm going to take angular moments of this RT equation. This partial differential equation, I'm going to take its angular moments. So what are angular moments? The 0th angular moment of a quantity is just its average on all directions. So I just integrate it over all directions on a sphere and divide it by 4 pi. That would be called the 0th angular momentum of a quantity. Similarly, the first angular moment is I multiply that quantity with the direction vector n and then integrate it over all the directions and divide by 4 pi. Similarly, you can have second angular momentums, third angular moment, and so on. Okay. So this is what the moment-based approach is going to do to this radiative transfer equation now. So how can we do this? We can write the 0th angular momentum by RT equation by simply integrating each term in the equation over all directions and dividing it by 4 pi. Now it turns out that when you do this, you get an entirely different equation which looks like this. Okay, so notice first that this equation has no I nu because now averaging has been done. Instead of I nu, what you have in this equation is this photon number density n nu, which is a moment of our I nu. Okay, so the equation is describing the time evolution of n nu instead of the time evolution of I nu. Except that you also now have this second quantity vector f nu, which is the first moment of I nu. This is the photon flux, okay, which has this expression. It is I nu times n, the direction vector n hat, again integrated over all directions. So now your 0th angular moment equation of our radiative transfer is just an equation of the time evolution of n plus some quantity about the flux, and on the right hand side we again have our absorption and emission terms suitably modified. So this is what this averaging has produced for us. Now notice that I said that the averaging will require us to make some assumptions. Now it turns out that if I have to write this equation, I need to assume that this kappa and j are isotropic. So that is a big, huge assumption that has gone into this step, right in our step number 1. Okay, but we carry on because now what the moment-based RT says is that you could in principle solve this equation numerically by applying numerical techniques for solving PDEs to solve for this quantity n, and it will tell you not I but at least the quantity n, the photon number density at each point as a function of time. But the problem is we cannot do that because we don't know f, we don't know the first moment. So what we do now is take the first angular moment of the equation. We have just taken the 0th moment. Now we take the first moment so that we can get an equation for f. That equation looks like this. Okay, now instead of del n del t, we have del f del t. Again, there are some absorption emission terms on the right hand side. But now we have another problem that we have now, we seem to have got a tensor term here where the tensor p shows up. Okay, this is called pressure tensor and it is the second moment of the specific intensity I. Okay. So now we have got the first angular moment of the RT equation, but if we were to solve that equation for F, we would need the pressure tensor. But how do we get the pressure tensor? We can now write the second angular moment to solve for pressure tensor. But then that would have a quantity which would require the third angular moment of the equation to be solved. But then we would to solve the third angular moment, we would need the fourth angular moment, and so on and so forth. We would need a hierarchy of infinitely many angular moment equation. So which is pointless. It seems that we haven't gained anything. So what moment-based RT does is, it says, hold on, things are not that bad. What you can do is you can stop at the first angular moment point. But then how do you solve for F? Then the method says you are going to solve for the F by simply postulating a value for the pressure tensor P. Instead of solving for P, you just postulate P, and then once you have a value for P, you just have a closed system of differential equations. Now, what value of P to use? That is a topic of a very large amount of scientific literature in this field, both around 1960s and 70s, and increasingly also in the current day. What I will talk about today is this particular choice of the pressure tensor P, which is called M1 closure. Okay, now this weird looking form of P is a particular choice. What is the physics behind this choice is a deeper discussion that we can have. It relates to the pressure tensor of Lorentz transformed blackbody radiation from a point source, but how is that generally applicable to a cosmological radiative transfer is not clear a priori. There is a lot of complication there, but at this point we will just say that someone has magically given us a value of this pressure tensor instead of us having to solve that infinite hierarchy of moment equation. Okay, notice that this pressure tensor is related to the 0th and first moment of the specific intensity F and N. Okay, the rest are just numbers. The sky and so on are just numbers, but essentially this form then gives us a value of this pressure tensor P at each point in the cosmological box. Once we have that, we have a fully defined, well-posed numerical problem. We have a system of two partial differential equations. One is a partial differential equation for n nu. The second is an equation for f nu. And if we assume this form for the pressure tensor, then this is a closed system of two equations. We don't need anything else. This approach to radiative transfer was first applied in cosmology in 2007 and 2008. So not that long ago. Okay, it was first developed for stellar radiative transfer back in the 1980s. It was first applied in cosmology only about 15 years ago. Okay. What I'm going to now demonstrate is how this is coded. In the spirit of this workshop, I will try to describe how this algorithm works in practice, and then I will talk about some results. What we want to do is we want to use this M1 closure algorithm, this M1 closure moment-based algorithm to study reionization. Okay, remember this cartoon evolution of the universe that I showed at the beginning. We want to study this epoch of reionization in which radiation from sources propagates in the cosmological volume. How do we do that? We do that by performing our moment-based RT on top of a cosmological hydrodynamical simulation. What do we mean by that? We go back to the kind of simulation that I showed a few slides ago, where you looked at this density distribution at a certain redshift. You can get such distributions at all redshifts, but you compute these distributions a priori using a cosmological hydrodynamical simulation. I believe there has been some discussion in this workshop on those kind of simulations. And then you say that that structure, that hydrodynamical structure, is what gives me my kappa and j terms, my sources and absorber terms in the radiative transfer exercise. And so we then put those sources in this box and compute radiative transfer using our moment-based approach that I just described. We do this using a code called Aton, which was written by Aubert and Tessier in 2008 and 2010. Okay, it's going to use this M1 closure and moment-based RT exactly as I described just now. Okay, before I go into the details, just notice the dynamic range of the problem now. The box size is about 160 megaparsecs. When I run these simulations, I have 2048 cube cells in this box, which means that my spatial resolution is 80 kiloparsecs. So I now have about 4 orders of magnitude dynamic range between my in my problem. Okay, so this addresses those two one of those two challenges that I mentioned at the start of my talk. Okay, so we have set up a cosmological hydrodynamical simulation in order to study reionization. It has high dynamic range, and we are now going to run our ATON code, and by that means we are going to get our radiation transport done. What that means is we are going to solve our system of 2 partial differential equations with this assumption for the pressure tensor. Okay. Now notice, if you have studied any partial differential equations at all, notice that this is an initial value problem in partial differential equations, because this quantity n and this quantity f, both of these quantities are specified across the box at the initial point t equal to 0. Okay, cosmology gives us our initial conditions, and then all that we have to do is to evolve these things in time. So the initial value problems in partial differential equations have many numerical techniques available to solve them. And so what ATON does is it says, okay, let me solve these equations by first setting their right-hand sides to 0. The absorption and emission terms, let me set them to 0, so that the equations take this homogeneous form, this simpler form, where del nu del t plus something is 0 and del f del t plus something is 0. This initial value problem can now be solved using many methods, but the simplest possible method is an explicit Euler method, right? I'm sure every one of you knows explicit Euler method, perhaps for ordinary differential equations, but it works exactly in the same way for partial differential equations. So ATON aims to do that. Except a slight problem is that the explicit Euler method is unstable, and so ATON has to use something else. But luckily, there is a variation of the Euler method known as the lax method, which is available, which is just a very tiny variation, a very small change to the Euler method, but it magically revolutionizes the stability properties, and the lax method becomes stable as long as this condition on the time step is satisfied, that the time step of the integration is less than delta x divided by speed of light, where delta x is your spatial resolution. This condition is called Courant condition. So as long as Courant condition is satisfied, your lax method is going to be usable to give stable results, and that is what ATON does. Okay. So in practice, we set this delta t ourselves, and then for that delta t, ATON uses the lax method to evolve the homogeneous partial differential equations written here. Except that what happened to our right-hand sides, right? The absorption and emission terms have vanished, so we need to do something to them. So what ATON does is it applies only one time step of the lax method. It takes only one time step with the lax method. It updates the values of n and f throughout the box, and then it turns its attention to the right-hand side. The right-hand side is essentially the radiation matter interaction, right? The way the radiation interacts with absorbers and emitters of radiation. And this is essentially the equations of those kappa and j, except that if I now write down kappa and j in terms of cosmological quantities, the equations become something like the first 2 equations shown here. So the first equation is now showing us how the quantity n changes with time because of the source and absorption terms. The first term here is an absorption term, which says that photons get consumed because they are used up in ionizing hydrogen atoms. The second term says that photons also get replenished because ionized hydrogen atoms recombine by some probability and produce new photons. The third term says that new populations of photons can be added to the problem because of new galaxies turning on. And the final term says that the number density of photons is going to change simply because the cosmological volume expands due to the universe expanding. Similarly, you have a second equation for the flux F, where again you have terms which describe ionization and the Hubble expansion. Now, a complication is that the story could have ended at this point, but a complication is that these terms these kappa and J terms, these ionization and absorption terms, have various quantities which depend on the neutral hydrogen density and the thermal energy of hydrogen or the temperature of hydrogen. So we also have to solve for the chemistry of hydrogen and the temperature of hydrogen. So we also have these additional thermochemistry equation to solve. For this particular talk, the thermochemistry part is kind of not that important for our discussion. The only reason you have to do that, the only reason I have to mention it at all is because it's necessary to write the radiation matter interaction terms. But in any case, given these four equations, you have a situation where you can solve these four equations using an Euler method now. That is what ATON does. ATON uses a combination of explicit and implicit Euler methods for these four differential equations, and it takes one step of these. And this step is going to do this thermochemistry and radiation matter interaction and update the values of N and F. Then it goes back to the radiation and takes one more step of lax. Then it comes to this, does one more step of radiation matter interaction. Then it goes back to radiative transfer and takes one step of lax, and so on and so forth, and until it reaches the end of the problem. What is remarkable, as I said, was that this pressure tensor has this amazing property that it is local. A pressure tensor at a given point, because of our assumption, depends only on the values of various physical quantities at that point. This locality allows us to split our problem into multiple subcubes. This huge cubical volume, which has to be huge because of the dynamical range requirements, can be split into different subcubes, each of which can be sent to one individual computing node for this integration using Lax and Euler. Okay, this means that the problem is readily parallelizable. Okay, so that's one thing. The second thing is our initial conditions are easily specified by cosmology. There is no problem with that. For those of you who are interested with the details, the third point is relevant, which is that the sources, this n star dot or the J term, that can be slightly complicated because the sources and their luminosity depends on the complex astrophysics, which I have not described so far in this talk. In the simulation that I'm going to show, we simply assume that the sources live in FOF groups and each source has a black body spectrum. Okay, but the point is, with these specification, you have a beautiful parallelizable implementation of cosmological radiative transfer. Okay, now there are a couple problems. One is we made some assumptions while averaging, and second, we made an assumption for the pressure tensor. Given those two things, we can never be confident whether our algorithm is going to give physically correct answers. Okay, even if we get a beautiful computer and have a great time step and a great dynamic range, these algorithmic characteristics will cast a doubt on our quality of results. And so the first thing you have to do is to have the code pass many tests. But what kind of tests can you devise for a complicated computation like this? One test is comparing to analytical solution for simple problems. Okay, so you can see an example here where you now have a very simple radiative transfer problem where you have a simple uniform source at the center, and you are looking at how radiation expands in a shell, in a spherical shell around that source. Okay, and the radius of this, the time evolution of the radius of this shell is shown in the right hand side plot here in the top panel in some units as a function of time, again in some units. And the interesting thing is this time evolution can be analytically computed. Okay, in fact, the bottom panel shows the ratio between this numerical computation and the analytical computation, and you can see that we have a result that is better than 5% accurate. So this is one kind of test that you can come up with. The other test is you can come up with a comparison for complex problems where there are no analytical solutions. You could compare the code results with results of, say, the brute force radiative transfer solutions, for example, from ray tracing. Okay, even that doesn't exhaust the testing. Even that will never make you 100% confident. So there is always work underway to develop better and better tests to ensure that our assumptions that we made are correct. Okay. But anyway, having made these tests, having achieved some relative degree of confidence, we can now hope to see some results, and here are those. Okay, so this animation will show you how radiation transfer looks like when solved using this M1 closure method. What is shown here on the right-hand side panel is the temperature in our cosmological box. And in the left-hand side panel, you are seeing the distribution of ionized hydrogen. And you can see that there are millions of sources in this cosmological box, and each source is giving out this radiation. This radiation is propagating on cosmological distances. It is reducing neutral hydrogen density. It is heating up hydrogen, and then slowly these regions are overlapping. And by redshift of 5.3, you find that the whole cosmological volume is ionized. Okay, so this is the result of the computation that we have achieved. Now you can see that the method does capture growth of ionized regions and their thermochemical equation to some degree, right? What I did not describe so far is that we actually do this computation on GPUs, on graphics processing units, instead of CPUs. I believe there has been discussion on GPUs in this workshop. And again, the idea is that this M1 closure is local, that pressure tensor that I wrote down was local, and therefore, this is ideally suited to parallelization. And GPUs are fantastic with their the hierarchy of tasks that they have inside them and memory associated with those tasks. GPUs are like an excellent MPI machine in themselves, and so you can use GPUs readily with Aton. In fact, that gives a huge boost in speed relative to CPUs. So this figure on this slide shows the execution time for each time step, this Lax and Euler time step, as a function of different values of number of cells in the problem. The red points and curve shows the execution time for CPU-based computation, and the blue points shows the execution time on a GPU-based computation. And you can see that this is already a more than almost 2 orders of magnitude enhancement in the speed of the calculation. And this test was already done more than 10 years ago on a GeForce GPU. Since that point, GPUs have developed far more in their computational capacity relative to CPUs. So if I were to do this test today, I'm sure the difference in the execution time would be even more. In fact, for the kind of simulation that I showed in my animation, we require about 700 hours of time on GPUs on a modern NVIDIA Pascal 100 GPU. Okay, the code has another property because of this beautiful averaging, is that it scales quite well. So I'm sure that in this workshop, people must have developed familiarity with strong and weak scaling. So what is shown in the left-hand side here is a strong scaling study of a very small simulation. Certainly nothing comparable to this big simulation that I showed, but that small simulation the simulation size was kept the same, and I kept increasing the number of nodes or the number of GPUs that I used on the x-axis, and I noted the speed up relative to a 1 GPU computation on the y-axis. The blue curve shows my result. The black straight line shows the perfect scaling in the ideal case where the job is embarrassingly parallel. And so you see that the strong scaling shows that the code scales quite well up to 40 GPUs in this small example case. The plot beautifully fits the picture you expect from Amdahl's law, if that is discussed in this workshop. And now you can look at the weak scaling, right? On the right-hand side, what I show is the weak scaling of the code, in which you keep the problem size per GPU the same, and you keep increasing the GPUs. And now I go all the way to 512 GPUs. Again, the expected behavior, the behavior is following very well the expected Gustafsson behavior. But now you can combine the information we get from the weak scaling plot to the strong scaling plot and find that for a cosmological simulation of the size that I showed in my animation, you have a very good scaling up to 512 GPUs. All this is the miracle of the mathematics of the isotropic and local pressure tensor. Another interesting feature of this whole machinery is that you remember that there were 2 steps, right? There was one lax radiative transfer step, and then there was a thermochemistry step. It turns out that the lax step takes most of the time, which means that our hard work on developing the M1 closure algorithm pays off. And this is shown in this diagram where I show the cumulative time taken by the code in its run on the vertical axis, and the number of these time steps, lakhs time steps in units of 1,000 in the horizontal axis. And the purple line shows the total code running time. The blue curve shows the time required by only the lakhs steps, only the radiation transport steps. The other curves show the time required by the thermochemistry step and other things like input, output, and so on. And you can see that the radiation transport accounts for the majority of the computing time, which is good news because radiation transport has the best algorithmic behavior, the most well understood algorithmic behavior in this code. Okay, so what we have seen so far in this talk is we saw a description of a particular moment-based radiation transport code called M1 closure algorithm, and then I described how an implementation of that algorithm in the ATON code was used to produce a simulation, and we saw a result from that simulation. What I want to do now is to show you some scientific results from these simulations. Are we doing these simulations just for fun or just to make animations, or is it resulting in some scientific result which we could not have obtained without this computation, right? So I'm going to show you 3 results now. The first result is related to something called the Lyman alpha forest. Okay, so I'm not sure how many of you are familiar with what is Lyman alpha forest. Lyman alpha forest is a feature that you see in the spectrum of a high redshift luminous bright cosmological source. Okay, for example, there are these galaxies called quasars which are extremely bright, much brighter than a typical normal galaxy, and these galaxies you can see from a large distance. When you take the spectrum of this source, and this quasar is located at a cosmological distance, the spectrum shows a feature called Lyman alpha forest. This feature is shown in this diagram on the slide here. What I have shown here are 2 spectra. The spectrum is just a plot of the intensity versus photon wavelength. These are 2 spectra of 2 different quasars on the sky. The quasar for which the spectrum is shown in the top panel is located very close to us in distance, and the quasar shown in the bottom panel is located at a cosmological distance, at a very large distance from us. And you see that in the quasar that is located farther, there is a dense network of these white absorption lines on the spectrum, okay, which is absent from the top panel. This feature, this dense forest-like network of absorption features, is called the Lyman alpha forest. Now, the reason we are talking about the Lyman alpha forest here is that the Lyman alpha forest is a super sensitive probe of the matter density distribution of the universe, because the structure of the Lyman alpha forest is decided by the intergalactic medium, the distribution of matter, these filaments and so on between galaxies. Okay, in fact, these absorption lines in the Lyman alpha forest are governed by the cosmological density structure on the one hand and the gas physics on the other. And as a result, a study of Lyman alpha forest can be used to study cosmology as well as astrophysics of the intergalactic gas. Okay, it can also be used to study how the universe is evolving as a whole. It can also be used to study processes like reionization, which occur on smaller scales. So this is the Lyman alpha forest. Before I proceed, one bit of technical information is that the absorption strength of the Lyman alpha forest is called effective opacity. Okay, it is referred to as tau effective. It just means that if tau effective is large, then the absorption is very high. The Lyman alpha forest is very strong. And the reason I have to mention this is because I want to show you this plot. Because it turned out that after around 2015 and later, there was a puzzling behavior was seen in the high redshift Lyman alpha forest observations. And the behavior can be explained as follows. If you look at the left-hand panel for the moment of this diagram, ignore the right-hand panel. What is shown here on the vertical axis is this quantity tau effective, which is just the Lyman alpha absorption strength. How strong is the Lyman alpha forest? If tau effective is large, your Lyman alpha forest can be so strong that it wipes out the quasar spectrum. If it is small, then you can see these some absorption lines, but you still see some spectrum. So you see that this vertical axis shows the value of the strength of the Lyman alpha forest, and the horizontal axis shows the redshift, roughly between 5 and 6. And each point on this plot shows a measurement from real astronomical data of measurement of tau effective. And what you're seeing is that as you move from redshift 5 to 6, you clearly see that the tau effective increases from about 2 to about 5 or 6. Now, that's interesting, but it turned out that what is even more interesting is that although the value of tau effective increases, the scatter around the mean tau effective increases even more. That was a puzzling observation. And this point is made a bit more strongly in the right-hand panel. So if we can look at the right-hand panel of this figure now, you will see that what is shown here on the x-axis is now this tau effective, this Lyman alpha absorption strength. And on the vertical axis, what I have plotted is the cumulative distribution function. There are 6 curves on this plot, or 5 curves on this plot. They refer to distinct redshifts from redshift 5, 5.2, 5.2, and so on. What you notice is that the cumulative distribution function at redshift 5 is almost vertical, which means that at redshift 5, there is very little spread in the tau effective values. But at higher redshifts, at redshift of about 6, the curve is really, really slanted. What that means is that the spread becomes much, much larger. The shaded region here just show the measure of the uncertainty. It's not important for this discussion right now. What is important is that the curve is vertical here and it becomes slanted here. So at redshifts greater than 5, we have this discovery that the Lyman alpha forest shows large spatial fluctuations. Now, the question is why, right? And so various theoretical models were postulated to explain them. All the models failed. And so what we decided was that we decided to study the Lyman alpha forest by the means of our cosmological radiative transfer. So we set up a simulation, this large simulation that I showed, and then we examined what Lyman alpha forest does in our simulation box. And when we compared our results to the data, we found this. What you see here now is that the blue regions show the measurements from our cosmological simulation, the animation that I showed, and you find that it agrees with observations really, really well. And so what this means is that our GPU-based radiation transport simulations really achieved a sweet spot of speed and volume. They successfully overcame both of those challenges that I started my talk with. On the scientific side, the simulations explained these spatial fluctuations in the Lyman alpha forest due to delayed and patchy reionization. What do I mean by that? What I mean is that the simulations now tell us that if the Lyman alpha forest is seen to have these fluctuations, then reionization should look like this. What is shown here is the evolution of the universe in this model from redshift 8 to 5. The horizontal markings show the redshift. The upper horizontal markings show the corresponding age of the universe in mega years. These plots are called light cone plots, and the vertical axis is just a spatial scale. And what the top light cone is showing is the evolution of the neutral hydrogen content of the universe in our simulation. The middle light cone shows the evolution of the hydrogen temperature, and the bottom light cone shows the radiation flux in the simulated box. What's important is that the simulation is now teaching us that the reionization must have ended at around redshift of 5.3, 5.5 if the Lyman alpha forest looks the way it looks. Okay, and there is also a lot of information here in terms of the spatial structure, which we could not have had without doing this radiation transfer. Okay, now in fact the significance of this result was not simply because it agreed with the Lyman alpha data. It turned out that this simulation gave us, for the first time, a concordant reionization model, which seems to agree with almost everything that we know about the higher redshift universe. Okay, it's the first time this has happened. Now, I'll just show some examples without taking too much of your time. On the left-hand side panel here, what I'm showing in the vertical axis is a quantity called QH2, which just means the volume fraction of the box occupied by ionized hydrogen region as a function of redshift Z from redshift 4 to 12, where the blue curve is now our simulation result, right? There is very little ionized hydrogen at high redshift, and there is a lot of it at low redshifts, and the evolution happens in a particular way. All the other things on this plot are inferences of QH2 from widely different astronomical measurements. And you see that all of these measurements are consistent with our simulation. This is remarkable, okay, because we did not tune the simulation to match this. This is sort of a bonus result. In fact, if you look at the right-hand side panel, this is another example where what is shown this time is the tau, which is the sort of effect that the reionization has on the CMB. Okay, and this can be measured from CMB observations. The red band shows their measurements at high redshift, and the simulated result shows the blue curve. And you see that the blue curve matches the observed number at high redshift almost perfectly. Okay, there are several other measurements which are also beautifully reproduced by the simulation. And essentially the reason I'm saying all this is because this is what is giving us confidence that in spite of the averaging, in spite of the pressure tensor, perhaps the model is telling us something about the universe at these redshifts. Okay, but that's not the end of the story. Simply because we now have a very high dynamic range, I think this, as far as I know, this is, I think, the biggest cosmological radiative transfer simulation in terms of dynamic range at the moment. You can do things that were not possible to do before. One example is CMB science, right? So here is one computation that we could not do using radiative transfer before. What is shown on this very densely populated plot is a quantity called CLBB as a function of this thing called L. What this shows is kind of the power spectrum of something called B-mode polarization of the cosmic microwave background sky. This is B-mode polarization is something that reionization can produce in the CMB sky, right? And you want to know how much of it reionization can produce. And so various computations were done of this quantity, but the red curve shows the first and probably the only radiative transfer computation. And you can see that it goes for the first time to cosmologically interesting length scales, L values. Okay, and this is important because now it tells us that it's very low and so on. This has significance for CMB science if you are into that kind of a thing. My point in showing this figure at this point is simply that this technique allows you to do this kind of computation. A second example is 21 centimeter science. Perhaps more people in this audience are interested in this. But again, 21 centimeter is another thing which has a dynamical range requirement. Again, you need a large box. Again, hard to do with radiative transfer. What is shown here is the 21 centimeter observable, the power spectrum delta square of 21 as a function of Fourier scale k, wave number k, at two redshifts 5.58 and 5.41. with the black curve being the prediction of our simulation, the gray dashed curve showing what previous models said, and the colored curve show the sensitivity of various experiments, right? And so what we are learning is we are learning that the simulations now make a really strong prediction for very large excess 21 centimeter power at these redshifts less than 6. This was not suspected by most people designing these experiments. So this is actually good news for these experiments because at these redshifts, the foreground problem in 21 centimeter science is relatively easier. And also the potential for synergies at these redshifts with JWST, LSST, Euclid, all these other telescopes is much better. Okay, and so this is another benefit that that the algorithm has afforded us. Okay. So I have said a lot of good things about the simulation and the algorithms. The situation, of course, is slightly complicated as always, like real life. So there are a lot of challenges. A lot of work still needs to happen. There are algorithmic, technological, and physical challenges going ahead. For example, is our M1 closure accurate enough? We don't know. Nobody has been able to show the accuracy of our simulations yet. I gave you a lot of arguments why we are confident that we have something reasonable, but that's not proof. There are some arguments in the literature that our simulations might not be accurate enough, that improvements are necessary. We don't know that yet. Is our dynamic range sufficient? We don't know that. As I speak, I am currently running a simulation that is a factor, an order of magnitude higher in dynamical range. We'll see if the results change when I do that. We don't know yet. We still miss some physics. There is this radiation hydrodynamics connection which is completely missed. We are coming up with some sort of hacks to solve this problem. So my point is that there are still a lot of interesting ways in which the whole methodology can be developed, and my group is busy working on many of these problems. So I think I'll wrap things up there. I hope that I have conveyed to you that what cosmological radiative transfer simulations are. I believe that these are increasingly essential in the area of SKA, TMT, JWST, the kind of large projects that many of the members of the audience will be interested in. I hope you appreciated the fact that this algorithmic innovation of the M1 closure and the technical exploitation of GPUs allowed us to do this fantastic big RT simulation, which gave us real scientific benefit. This was not just numerics for numerics' sake, but it gave some unique benefits. There are some future things on the to-do list. We definitely want to improve the algorithms. That's the main thing in the future. And currently what we are doing is running large suite of such simulations on the national facilities of various countries, as well as the commercial crowd here in India. I think I'll stop here. Thank you.
Thanks, Girish, for this wonderful talk on this very complex problem and elucidating some of the very nice facets of how things can be simplified. I'll open the floor for questions. Please raise your hand and then I'll ask you to unmute yourself and ask the question. So participants, if you have a question, please raise your hand. So while participants are thinking about some of the questions, Girish, maybe I'll just go ahead. So this nice simulation seems to have answered a lot of questions. Besides going to the CMP stuff, so what are the things that are missing? You have listed out a few at the end. Which is the next step that you would be really focusing on, for example?
Right. So I think it's always the usual catch, right? There are steps that I would be interested in focusing on, and there are steps that my abilities allow me to focus on. So what we are really interested in is understanding. Personally, my interest lies in understanding the accuracy of this algorithm. There are severe problems potentially on the accuracy front at the end of reionization mark. Unfortunately, we don't even have the mathematical tools to understand that. And so there is a lot of work to be done there conceptually. Unfortunately, although this point is of great interest, it is also the hardest. What we have been occupying ourselves with is pushing the dynamic range so far. So we have just done a 4096 cube simulation, and we are learning the challenges involved in that extreme dynamical range kind of a scenario. So those are the 2 points where we have directed our immediate attention.
Right. And just before I go to the participants, so it is again related to the M1 closure, I guess. And M1 is a fantastic scheme, but I guess it is not so robust for multiple sources. So is that loss of accuracy also there coming in because of that at the late phase of the reionization?
So what you are saying is partly correct, but the situation is slightly complicated in a very interesting way, which is that M1 is accurate for one source. It is very bad for few sources, and then it again becomes accurate for many, many sources. So that's why it appears that when you have millions or billions of sources, M1 is not that bad, because sort of the ionization structure cancels things out in a particular way, which is why the M1 might still be okay for us. But this transition is something we would like to understand better, from few sources to many sources.
Right.
But you're right. For example, just for two sources, M1 is a miserably bad method.
Right. Right. Thanks, Girish. I'll get to the participants. I have a few hands here. So, Satyaki Goswami, please go ahead and ask your question.
Thank you, sir. Good afternoon. Sir, my question has two parts. The first one would be like when you were talking about averaging each and every component of the radiative transfer equation. So does that averaging is limited by the number of dimensions? Like the last integration would be over the volume?
No, the way I described it, I never bothered about the volume. My integration was always on the angles. So the quantities had complex volume dependence, but we were only integrating on the directions at each point.
Okay. Over the sphere, sir, like as you said?
Yes, yeah, over all the directions.
Okay, sir. And sir, the second part is a little bit general question, sir. Like, these kind of simulations are they also applicable for accretion processes and all?
So that's the kind of, it's related to the question that Dipanjan asked as well, which is that I think the answer is because we don't have a conceptually robust theoretical understanding of the algorithm. There are cases where it can work and cases where it cannot, right? So one would have to, my answer would be, you have to test and check. The typical sort of warning flags that I would raise is that this whole system fails when there are few sources, but it works if you have many sources. The system also fails when you have few photons. Because, so I didn't have time to go into this, but this average equation actually look like continuity and Euler equation of fluids. So when you have, for example, very high energy photons, that a fluid approximation looks a bit ridiculous. X-rays do not, X-rays behave more like particles than sort of a fluid. And so there are aspects of accretion disks, radiative transfer, where this would not be a suitable algorithm, is my gut feeling.
Okay. Well, thank you, sir. Thank you very much.
Thank you, Shatuki. Shubham, please go ahead.
Thank you, sir. Thank you, Professor. So, sir, my question is, it might be a very naive question, or might be I'm very confused. So, this is just on the cosmological evolution of the radiation throughout the cosmic history. Like we are using the cosmological radiative transfer. So, my question, like I'm doubtful on that. Like, what about if we include is the like other cosmological constant, like the dark energy constant, the constant in the equation of the cosmology. So is that included in this cosmological evolution or is not? If it's included or not, and if not, then what effect would it have if we include it in the simulation?
Yeah, so all that's included. That's just included in the Hubble parameter that comes there, unless your modification is that radiation itself, in which case the inclusion will have to happen elsewhere as well. Short answer is that it is.
A lot of background noise from your end. Were you able to hear the answer? Or do you want to ask anything else?
Hello. Yeah. Yes. The voice got feeble. I didn't actually got the answer. So,
Okay.
The short answer is that the kind of modifications that you are suggesting are included.
Okay.
Okay. Thank you. Thank you.
Ayush, please go ahead next.
My questions are, well, can you please go back to the slide where you compared your Z greater than 5 simulations with the data?
This one?
Yeah, so there's loop patch in the right panel at the bottom one. Why is that like there's no corresponding orange patch to that? Is that because you simulated conditions that were not studied observationally?
Yeah, it is a prediction of the simulation, right? It is a redshift at which no observations were available at that time.
Okay, I'm sorry for that. Another naive question would be, so I didn't understand what the physical reason was for this puzzle at greater than 5 redshift. Can you explain that briefly?
So a simple way to understand it is basically that the reason there is a large scatter in the Lyman alpha forest is because the things that produce Lyman alpha opacity, namely the neutral hydrogen density, it has a lot of structure. And the structure you can see in this plot on this slide. So what the simulation is telling us is that the simulation is showing the structure which can result in the kind of spatial fluctuations that you are seeing in the data. So the simulations are saying that the observed spatial fluctuations in the Lyman alpha forest is because a spatial an unobserved spatial fluctuation in the neutral hydrogen density of this kind at this redshift. That's the physical reason. Okay, so this is not an obvious fact, right? It could easily have not agreed. You could easily have fluctuations, you could easily have structure without agreeing to the data. So the remarkable thing is not only does the simulation give us the structure, it also agrees automatically to the spread that we have seen in the data. That's the remarkable thing.
Okay, and thanks Ayush for your question. Sumit Banerjee, please go ahead next.
Hello, am I audible?
Yes, go ahead.
Thank you. Girish sir, I have a question regarding the dark ages. I believe the radiative transfer equation gives us the entire evolution of how the universe evolved over the time. Now, the thing that I'm struggling to understand is the very reason it's the dark age that is called because it remains outside the horizon. So how do we use some kind of a mapping or any bridge between what we observe and what we cannot observe, and then try to run those simulations, or how exactly do we account for those periods?
Yeah, so the simulation basically switch on the sources at t equal to 0 of the simulation, and then they propagate the radiation. So by definition, we only simulate anything that is within the horizon. So the dark ages won't be affected by this simulation, right? The dark ages are outside the horizon of the sources that we are studying here. They are behind, so to speak.
Okay, so related question again. So if we are starting with the sources which are within the horizon, then the very reason that the cosmos is expanding would also impact the total energy that is transferred from one epoch to the other, because obviously the wavelength increases, the energy will come down. So how is that incorporated in those equations?
Right, so that's incorporated by the Hubble term. I had this Hubble term in the radiative transfer equation that incorporates the fact that the number density of the photons at a particular wavelength will change. So one complication is that these simulations are monochromatic. So the question becomes slightly interesting for sort of polychromatic simulations. But for monochromatic simulations, the effect is incorporated by the Hubble term that I showed. So you are absolutely right. What you are saying will happen, and it's incorporated by the Hubble term that I showed.
Okay, thank you.
I think you are muted.
I'm muted. So Satyaki, you had a last hand up. Do you still want to ask a question, or you forgot to lower your hand? So I guess that is it. So thank you, Girish.